describe the experiences, and I'll have some closing comments at the end. Okay, I hit the arrow down. There it is. I'm going to populate this with a couple of background slides while the focus of the presentations primarily our COM experience. Let me put this in context a little bit. I fly a variety of balloon, suborbital, and orbital missions. In fact, I note that my Wallops colleagues, Steve and Brian, are on the call as well. They helped us with or flying the earlier Sorex 6 and 7. I think we had an LCT-2 there that Steve and Brian had produced. And then later on, we tackled the problem of how to get things on and off the space station, which was at first an arduous task. But now, basically, we have a pretty good flow on how to do that, and the result is that we have a pretty good workhorse that allows us to test a variety of things. Most of my TechEd Sat PhoneSat work has recently been involved in what we call an exobrake. This is a means to deorbit without using propellant, which I also like and teach propulsion courses. But this is an electric propulsion analog to using this, and it's fairly innocuous. That's why we can get on and off. But a couple of quick things is most recently with the one that's deorbiting right now, is our first attempt to actually modulate the drag, which means we can steer it. And why this is important is it really drives our COM, and I'll mention this momentarily. In terms of the thermophysics, if we get a ballistic coefficient, M over CDA of around 5 or 6, we basically get deorbit from the space station in about 4 weeks from 400 kilometers. One of our next missions, we will get a ballistic coefficient of about 1 kilogram per meter squared, which is about within a week from ISS or 8 weeks from 500 kilometers. That's something we want to demonstrate. Okay, so as far as the COM, what's the requirement? Well, our first here is that we really need to have an uplink or downlink capability once per orbit, and also have a GPS update per orbit. And this is essential in driving this, and again, drove our COM architecture quite a bit. So that's for quick command and control, and Iridium permits us 300 bytes per burst, and we'll describe that momentarily. But at the same time, we're also investigating we have an active ISM band development right now, which gives us an inexpensive 1 to 3 megabits per second. We would actually, with Steve in particular, Bundick, we hope to test this X-band capability that is an outgrowth of colleagues from Planet Labs, and other options. We're looking at optical and other things as well. But those fit on top of it, an ability to be able to command and control once per orbit, which is our desire. Avionics, I'll just talk about this momentarily. It's a 3.5U CubeSat that we're able to build. Our paradigm allows us to build 2 or 3 or 6U without any problem, and then you'll see that momentarily. Real quickly, this is what our anatomy looks like. So it's based on a extrusion. This has allowed us a lot of flexibility as far as being able to take advantage of transport holes that appear in the ISS manifest. But in particular, we have, because this is in part a cleverly designed reentry or a deorbit experiment. We have an ablator, a simple ablator on the front and to the left, under which we have our GPS, our Iridium primary patch antenna. So we call it Iridium number 1. Iridium number 2 is orthogonal. It's you see that Iridium antenna number 2 on the side there. And part of the reason for that was redundancy. And second is we actually dive into the atmosphere. Then the Iridium number 1 is nadir pointing. It's not going to see very much, which we'll see momentarily. And then Iridium 2 would give us some of the data that we need during that final passage demonstration. Architecture is following, as you guys know, and I think Globalstar is the same way. But we're able to basically command and control our nanosatellite through simple email ground commands. We do that primarily through our power board. And you see the Iridium 1 in green, and then that controls through regulators what we call a crayfish, and our PhoneSat 5 board. PhoneSat 5 actually is it's Intel Edison based, and that gives us an upper tier avionics capability that allows us to do a variety of things. Let me go again. Well, I'm going to back up a little bit. Well, momentarily you'll see the different avionics and some of the things we have going on. So here we have our power board, which is an Arduino Pro Mini, and just as an odd note, an important note is the ATmega family is surprisingly red tolerance, around one single event upset per 400 years. So we found it to be surprisingly robust. We also fly a teensy on a crayfish. We were flying the Intel Edison, which we've been pretty pleased for, and also we're developing actively wireless sensor networks as well. All these feed into our avionics comm stack, and then down to the ground for the low data rate capability. Now that's one of our EDU stacks that you see there. Fairly simple to build, and again, it's a robust workhorse flight experiment capability. COM as you see here, again, we communicate to the Iridium gateway. One of the things is it is not a bent pipe, which I believe the Globalstar is a simple comparison. So we have been using the short burst data modems, both the 9602 and not so successfully the 9603, but it's worked well. Real quickly on the wireless sensor module demonstration, you've seen advancement from the SORX #1 data collection I did about 18 years ago to the slow progression from suborbitals to most recently what our platform for the Gen 2 looks like in comparison to my lost car keys. Okay, so our first orbital experience, we tried this on balloons and suborbitals. This is actually the data for our TechSat 2. This is a fairly simple experiment that we had coupled with one of our phone sats. It was about a 100-hour experiment, and we used this to compare to, essentially, we're collecting data. In this case, it was a temperature data, so each point represents also a Iridium hit or handshake. And so we found that this actually outperformed our original SDK-based analysis. So it looked like it was a very promising tack. It also warmed up Iridium LLC to the idea we would do this. TechSat 3, we also used two twin 9603s. It has a smaller platform than the 9602s, but it turned out both of them failed. So test 3 was a aerodynamic success, but we couldn't communicate to it. We went back to the 9602s for test 4, and this is some of the data that we got from LLC. So it shows basically elevation azimuth and the number of hits that we collect over a period of weeks. The test 4 was successful. It was not a drag modulated experiment, but it successfully, we hit our ballistic coefficient that re-entered in about 28 days. Now, we flew 2 antennas on this. The previous data showed the forward Iridium #1 patch antenna pointed forward in the direction of the flight velocity vector. So actually, this is probably one of the more interesting and telling of the slides in this presentation. So what we have is this is the orthogonal patch. So at some point, we actually command it with our Iridium #1. It turns on, and then we get these data hits is right before it re-enters the atmosphere. What's also of interest is we're getting these are packet counts per day. So you see that we get up to 400 packets per day, which is around what 22, 23 per orbit, which is more than adequate. So this suggested a very healthy link margin and more than adequate for our needs. Now, I should also make note is that, and this will feed into the summary chart, but we don't know what, with this data, what direction it was pointed. Obviously not nadir, but it could be zenith, or it actually could be 90 degrees to zenith, to the right and left. But it did work well. We're happy with that. Now, if we jump to test TechSat 5, this is going to be a modulated device. We flew on, I think, March 6th. Everything turned on. All of our transmitters worked. Our avionics stack worked quite well. And also, I just showed in red down there, the onboard temperatures were more than adequate. We see our ablator temperatures over there, which are intended to be cold, and they are. But that worked. However, what happened was following. Due to we got ambitious with the design of our exobrake and went to a full drag configuration when we first exited the space station. But what happened is that we inadvertently discovered a metastable state that pointed us nose down. So if we look at our iridium patch antenna chart on the left, 0 degrees is our desired nose forward, which gives us actually pretty good result. But in fact, because of this anomaly, we were pointed about minus 90 degrees, so that we lost more than 10 dB, maybe 12 dB in our ability to transmit. And so if we look at our initial graph there on the right, we see the number of hits per day. We weren't too worried about it at first because we saw a slow trending up to the expected, 100 plus. And then what also happened in this particular case is that because we were nose down, we inadvertently discovered an asymmetry in our ability to be able to send an uplink command. So the uplink command that we anticipated would have allowed us to essentially change the drag configuration, drag state of the exobrake, giving it a larger aerodynamic moment, and then pointing it nose first, nose forward as it was intended. It turned out that we got stuck in this, so this was an ops trap that we didn't expect. It's been corrected. The test 6 addresses all this by design, and then we'll be able to move forward. Just a solar panel temperature graph. So we got a lot of data out of this. Also our new solar panel designs, which we're pretty happy with actually. Just a real quick note on SDK iridium coverage. My colleague Rick Alina has been doing this. We'll present more detail at the SmallSat conference in August. But basically, I showed that apparently there's 2-hour gaps just due to missing satellites in the constellation. This probably will be addressed by the new satellites coming into the constellation and also be included into the STK analysis. But that's what we were looking at. But again, with the 67 or 68 satellites in the network, it's pretty adequate coverage. And basically, we're trying to also ascertain, understand the link a little bit better. So we've been doing a variety of analysis to look at, okay, is this what are the Doppler and proximity effects, and what does the link actually look like? Again, we'll present that a little bit later on. And this is the elevation from the test 5 to the iridium satellites up to about 4,000 kilometers. So this is basically a work in progress. So the idea at first was that from our nose-mounted patch antenna, that we would ideally be able to close the link and be able to see all these, in addition to the ones orthogonally. Then nadir pointing, and that's and it turns out if we're at the horizon or a little bit below, that we can still close the link. Okay, so future missions, again, this is an active flight laboratory, and with our SSTP sponsors and other people as well. The intention was to build 5, 6, and 7, and 8 fairly quickly. And so you see test 6 there actually that we're currently in finishing, and we'll have it ready for flight or for handover late August. Test 7 that you see in the middle is a 2U. We have an opportunity to fly a 2U, which enables us to build a different version of our exobrake, which allows it's more compact, and therefore we can achieve a lower ballistic coefficient, higher drag. So we're reaching a 1 kilogram per meter squared for a rapid or disposal demonstration. And then test 8 is something we would we're building as well. It's a 6U that we're able to fit into an NRCSD 6U dispenser, and that enables us to include a couple more experiments in the avionics stack, but also a few other common experiments we want to propose. Summary. Again, all this is work in progress, but our TechEtsat N and PhoneSat it's a rapid prototype workhorse, as you've seen. testing a variety of things, including COM, and that's, I think, part of the interest of this working group. The exobrake itself is advancing quite well. Future applications include accurate deorbit and disposal from 400 or 500 kilometers. I didn't include the slide, but one of the interesting things is we find numerically that by modulating or changing the position of the exobrake 7 times during deorbit, that we can hit a 100-kilometer target at the von Karman altitude. So this actually is quite promising. How am I for time, Bruce?
Come on, you go.
Oh, okay,
yeah,
good.
Finish your slide.
So again, this is very anecdotal, but the short burst data modem works well and is our current COM baseline. We're anxious to learn more about Globalstar, but just as you've noticed, we can get 1 to 400 hits or downlinks per day, roughly 22 per orbit, as you see there. And as far as our TechSat 4, we had 25 of 25 successful uplinks. That was not the case for number 5, but we've had generally pretty good experience with it. 5 has that ops trap that I mentioned. And then the position of the forward patch antenna basically is really that way because it's an artifact of the exobrake development. Now the game changes as we change the antenna itself. I like patches because of the plan form, but we can go to a deployable stub just as easily, and that's something that we're actively trying to explore. And anyway, it's what we have is more than sufficient for the deorbit systems development I showed, and particularly the autonomy that we want to develop in the next couple of nanosatellites. And then also we're using that as a Mars analog relay. So I just have that teaser slide on the far left or far right. We're interested in nanosatellites on the surface of Mars and have devoted a lot of time and attention to that. So at present, we can't make a full and fair comparison with Globalstar, but we certainly invite that. Just a couple of off comments, and I think Joe and our FRL colleagues will certainly elaborate upon this, but it's the iridium is not a bent pipe, and what that is it does permit greater uplink opportunity and greater interval as well. I believe that's correct. The iridium does have twice the constellation size with fewer exclusion zones. That seems to be evident. And then again, as I've mentioned, the iridium uplink downlink has been very adequate for the kind of experiments that we're doing. It's not a panacea. We look upon that as for quick command and control, 300 bytes per burst. As we look at other higher data rate capabilities in the XS or optical bands, which need to be further explored. But this is a nice command and control platform. What I think we recommend is we should have a friendly COM comparison and keep on developing these capabilities and really understand how they work. And so we'd like to fly, like we suggest, 2 pairs of patch or stub antennas on maybe TechSat 8, where we would then know the roll orientation and can actually add to this otherwise anecdotal information I'm providing. And then, so I mentioned that. So the TESS 8 has 6U has room for some more experimental COM or other development, and we'd like to, approach our colleagues at SSTP to maybe help fund this so that we can really wring this out and understand maybe the differences and maybe mutual capabilities of these and other systems. So,
okay, I got one question to start off with. We have time for a few questions. Kyle's on his way over here now. If he gets here, great. We'll start with Kyle. If not, I'll ask Joe to go in next. But programmatics with the frequency allocation, how has that been?
It was a struggle for Test 5, to be quite honest. So we had to basically move from our previous model. By the way, what I didn't mention, and maybe you saw in some of the other slides, that we're also an active STEM and young career professional education or experience opportunity as well. And so we're trying to put forth a Space Act agreement that would enable us to more easily work with academia and other organizations to include a experiment subsystem or sensor in it. Our previous paradigm was that we would then go to the FCC as a hybrid, and there was no problem. So we had that worked out quite well, but the FCC has dictated that they don't permit any hybrids anymore. So everything we have is now through the NTIA. So our colleague Bill Notley here did a superb job in getting us in setting up the precedents for our NTIA submittals. So finally we got that. We were first yellow tagged for the ISS, but that was removed. We were able to turn on all of our transmitters for test 5, and then the NTIA submittals for test 6 and 7 are already in place and in progress. So once we establish the precedent, then I don't find that it's going to be of any problem. I should also make a quick note that I didn't, and that's some of our Japanese colleagues also, I think, were inspired with our design, and so one of their reentry satellites called EGG or EGG reentered earlier this year and also used a nose-mounted Iridium patch and GPS. But we haven't not been able to ascertain how well that worked for them, but we assume it worked well. But bottom line is that, with a little bit of practice, all this has been able to be worked out both programmatically and technically.
So we have time for a couple questions from the web or from the line for Mark.
Yeah, I have a couple of questions. Thanks for this presentation. Maybe I missed it, but what is the data transfer rate over Iridium with the patch antenna that you're using?
I'm sorry, who is this, please?
This is Charles Norton from JPL.
Okay, hey, Charles. Well, to first order, Charles, it doesn't really matter because it's basically you're just permitted. It's a short burst data modem, and so it's really not intended for, I think, a lot of data transfer. You probably can squeeze that if you do the right software, and if we parse up the data quite a bit. But it's the handshake occurs in tens of milliseconds, and that's all you get. So our interval is that we basically it's a kind of a stochastic comlink, if you will. So our interval is about we try to handshake once every 30 seconds, and then the overall success rate appears low, but in fact, if we can get 22 handshakes per orbit, as evidenced by one of our slides, then that's more than adequate for our needs. I don't recommend it, and I don't think it's intended for much heavier use. We want to use this to really turn on or off other S-band, X-band relays that would give you the higher data rate. Does that answer your question?
I'm not sure. I heard you say at one point 300 bits per burst.
300 bytes per burst.
Bytes per burst. So you're saying if you can perform this handshake 22 times per orbit, you can do 22 times 300 bytes of data transfer per orbit.
That's correct.
Is that correct? Yeah, that's what I'm trying to get at.
Yeah.
And
now, if you really want your data, I do recommend flying over the ground station, as we have set up with NASA Wallops, and then we can pipe down a lot more data a lot quicker. So I don't think this is a panacea for large data sets.
Yeah, I'm just trying to understand it. So what would be the Wallops connection in this case? Are you saying there's an opportunity over Iridium to increase the data rate by using a Wallops ground station?
No, sir. It's not for Iridium, but for the other COM experiments, basically SXL or not L, but ISM band. We have an active experiment with there to get 1 to 3 megabits per second with essentially a hacked Wi-Fi transmitter. That's an example.
Yeah,
so we're dependent on the large dishes that NASA Wallops has, and their kind permission to work with them to actually have a better, higher data rate pipe pointed down. We also tried this with the X-band on our suborbital, starting off with an intended 10 megabits per second on the NEN dish, and we'd like to try that again, but that's just as an example of.
Yeah, I'm primarily interested in the Iridium capability just for now.
Okay, it's 300 bytes per burst. Roll the dice, but it looks like it'll come up pretty well, up to maybe 22 times per orbit, which for a lot of things I think is pretty adequate.
And did you mention that the connection protocol is basically email requests?
Yes, sir. I think we're the first, Joe can correct me, but we're the first kids on the block to control their nanosatellite via our smartphone.
Unless Kyle did it.
Maybe Kyle did it.
No. Okay, great. So good questions all. Kyle's here. Yoo-hoo. I'm sorry about the mess